So in the preparation of alcohols via substitution and addition, this should be a pretty quick review of principles that we learned in first semester organic chemistry. So we learned that you can use an Sn2 style reaction with a good nucleophile and a primary alkyl halide to produce the substitution product. In this case, we'd end up with a primary alcohol, and that's an Sn2 mechanism. You should be able to draw that in your sleep at this point. If we look at a slightly different version of the alkyl halide, let's put a couple more groups on that carbon bearing the leaving group. Now we are looking at an Sn1 mechanism, of course, because we have a tertiary substrate, and in that case we need a weak nucleophile, so water would be a great example in this case. And after we draw the mechanism, we have a final proton transfer step. We end up with a tertiary alcohol as our product. So we can make alcohols via Sn2 or Sn1, depending on the shape or the setup of our alkyl halide. In the addition chapter, where we dealt with alkenes, we can add water across the double bond, so dilute sulfuric acid in this case gets us to the secondary alcohol, because we're adding water across the alkene here. If we use the same alkene and we use the hydroxymercuration reaction, we're adding the nucleophile water. The second step, of course, is reduction of the mercury. We end up with the same product. Remember that the difference here is that there are no cations formed in this mechanism. And of course, again, these mechanisms should be very familiar to you after studying first semester organic chemistry, and you can review them in the appropriate chapters earlier in your textbook. So again, using the same alkene, we can add water in the other fashion, which allows us to put the OH on the less substituted carbon. And if you were in my class for first semester, you'll remember that that's one of my favorite reactions. That's the hydroboration oxidation reaction. And this does anti-Markovnikov addition of water. So we end up with the primary alcohol instead of the secondary alcohol like we had on the first two examples. And you should be able to show us the mechanism of this reaction as well. That brings us then to the next section, which is preparation via reduction. So this is a new concept that we're going to cover in this chapter. First we need to talk a little bit about oxidation state, and that's going to be different than formal charge. So we talked about formal charge early in the textbook, early in Organic 1. And if you remember from that, we can look at formal charge like this. Here's methane. And there are 4 bonds to carbon, and we give carbon half of each of those bonds, so the carbon has 4 electrons around it. And we know that the valence count of carbon is 4 electrons, so that means there is a 0 formal charge. If we contrast that with a carbon with only 3 bonds and no lone pairs, we know that the carbon gets 3 of those electrons. Normally it wants 4 electrons, so we have 1 fewer negative charge than normal, so this would be a +1 formal charge. So we know that carbon with 3 bonds and no lone pairs is +1. This is not news to us. When discussing oxidation state, we treat the carbons and the hydrogens and other bonds next to carbon slightly differently. So let's look at methane again. So let's just make sure that this is oxidation state right here. We now look at sort of the electronegativity of the elements in our molecule. We're going to treat carbon as having a bit more electronegativity than hydrogen. So if we split these bonds apart according to electronegativity, we get something that looks like this. And I guess if you want to put the 4- around the carbon, that would be reasonable. And We know it's 4 minus because it normally has 4 valence electrons. Now it has 8, and so that's the oxidation state. So the oxidation state in this case for methane equals 4 minus. And the reason we are calculating these will become more apparent in a few minutes when we start actually changing the oxidation state of some carbon molecules. So let's look at methanol instead of methane and see how that would differ. In this case, each of the carbon-hydrogen bonds are retained by the carbon, but the oxygen is more electronegative, so it would retain the entire bond from the carbon. So in this case, we see that we have 6 electrons around the carbon. Normally we want 4, so the oxidation state is 2 minus. So we've changed oxidation states by going from methane to methanol. All we've done is add 1 oxygen, and you can see that that has resulted in an oxidation state increase of 2 units. And that's pretty typical of when we add oxygens to an organic molecule. Let's look at one further example. So here's acetone. If we're going to split these bonds apart, the oxygen takes all of the double bond electrons, and the 2 carbons that are bonded to the carbon, we can't say that one is more electronegative than the other. So in the case of the carbon-carbon bonds, they get split in half equally. Excuse me. So now you see that the carbon, the central carbon that we're looking at, so essentially all of these are we're focusing on this middle carbon here. We're going to do the same thing on acetone, even though there's more than 1 carbon. Now we have 2 electrons around our central carbon. Normally it likes 4, so in this case the oxidation state is 2+, where it only has 2 electrons around it instead of 4. And that comes from the extra bonds to the doubly bonded oxygen.